So hello everyone, welcome to the 12th live interactive session on geosynthetics and reinforced soil structures. So due to some personal reasons I could not take this session on Sunday, so we will be continuing with that today. And today is practically basically the technically the last live interactive session, and the coming Sunday, that is on the 20th, we will have just a revision session of 1 hour duration from say the same time 3 to 4 p.m. okay, in the afternoon say. Okay, so we'll have the discussion sorry the revision session on the Sunday, the coming Sunday, for 1 hour, and with that we will wrap up this course. And in today's session we will be just briefly we will briefly discuss about different technicalities involved in the use of geomembranes. Okay, so geomembranes, as you know, we had already discussed previously briefly towards the beginning of this course, right? So what are geomembranes? Geomembranes are nothing but they are generally a polymer. They are formed using polymers such as PVCs and nylon 66 and several other stuff. And so this basically mainly they are PVC, made up of PVC and some other materials too. So these are nothing but plastic sheet kind of thing, right? These are plastic sheet kind of things that are actually used for, mainly used in lining purposes. Okay, these are mainly used as liner purposes. So various some of the, not, we cannot actually study everything in detail, as our course is very concise course. So we will be just looking into some of the basic concepts that are there in case of geomembranes. Okay, so as I said, geomembranes are generally used where? Geomembranes are generally used for landfills. Okay, so in landfills, what do we do? In landfills, we dump the waste. We dump the waste. That waste may be industrial waste, or that may be MSW. That is the municipal solid waste. Okay, that waste may be anything. So that landfill is an engineered, okay, is an engineered thing or engineered structure that is actually constructed so that whatever you dump, okay, say you dump municipal solid waste, okay, so that the waste is contained within that landfill only. The harmful substances or chemicals which come out of that waste, which are known as leachate, that leachate should not come go and contaminate the surrounding ground. Okay, this is one thing. And one more thing is that the leachate should not actually go and contaminate the groundwater. It is much more important. So due to that, what we have to do, we have to design that landfill in such a way that it retains the waste within it perfectly. All right, so these are engineered landfills. So we have to use a lining system, right? We have to line the landfill with some material. So the lining may be made up of, say, various geosynthetic material such as geosynthetic clay liners, geomembranes, and other stuff. Okay, so let us see what is written. A landfill is an engineered depression in the ground to dispose of different types of waste. Okay, a landfill is an engineered depression. Engineered depression means it's just a cut up and dug out in the ground to dispose of different types of waste. So it is not that you just go and dug the soil out of that place and you make a hole and you dump everything. That is a non-engineered kind of thing, right? But what you have to do, you have to make it engineered landfill so that whatever you want to contain, it's contained within that part only. The harmful substances that comes out from the waste should not contaminate the surrounding ground or the groundwater. All right. So these are constructed with impermeable linings to prevent any leachates from migrating into the ground. The landfills are given a cap after they are completed and filled up with the waste. Okay, so we have to line this. We have to line the landfill with some liner material, as I said, maybe geosynthetic clay liner or geomembrane, whatever. And after that, we have also have to cover the landfill after the landfill is completely filled. Okay, after the landfill is completely filled, we have to design a cover system also. So why do we need to covers for landfill? What is the What is the reason? So usually that is given here. So usually landfills are spread over several hectares of land. So the area of the landfill is very huge. So if you see, if you so every city, every big or a small city or town has a landfill where all the municipal solid waste of the whole city is taken and dumped into. Alright, so if you visit the landfill in your city or town, you will see that the landfills actually cover a huge area. Okay, they cover a huge area. The area of over the landfills can be reclaimed by covering it in a scientific manner. Say landfill, you have constructed the landfill is completely full now. Okay, you have dumped waste over the years and now the landfill is completely full. Now how to use that area again? So what we can do, we can cover it with a cover. Okay, landfill cover, we can cover the landfill, and after that we can put soil over that and grow trees. Okay, that we can do. Also to prevent the ingress of rainwater or any surface water from infiltrating into them. So we also do not want that any rainwater or anything should not get into the landfill. Okay, should not get into the landfill. To preclude the formation of unsightly scene and okay. So one is, first thing is that to reclaim the land, completely filled landfill, we need to cover that. That is one. Second is to prevent rainwater from entering. That is the second one. And the third one is that we do not want to as get the order, bad order that comes out from that. We do not want that, right? And also we do not want that birds to, like vultures and all, what they do, they come and they take this waste, they will carry it, they will drop it around, they will just dirty the whole air surrounding it. So we do not want that. So that's why you use this landfill cover. Okay, so what are the different geosynthetics that we use for landfills? So first is the liner material. So liner materials, as I said, geomembranes and geosynthetic clay layers, clay liners. So geomembranes and geosynthetic clay liners both have very negligible permeability. They have low permeability to both gas and liquid. Okay, so they stop gases and liquid to pass through them. Then we need to have reinforcement. So you have the slopes of the landfill, right? So these slopes, if it's too steep, or if we are putting lots of dumping lots of waste over it, so there are chances that the landfill slope may fail. So we need to reinforce the slopes of the landfill sometimes. Okay, then you need to have a proper drainage so that whatever gases or whatever leachate is trying to seep out, that is actually taken, carried through the geonets and geotextile drains, and finally drained into a larger under drain. Okay, so you need to design a drainage also. And then we have the protection is nothing but geomembranes and GCLs are generally very sensitive, very delicate. So to prevent the damage of that, we actually place a layer of thick non-woven geotextile over that. Okay, just to keep it safe from any mechanical damage. Okay, and then we have at the last collection of leachate and gases, that as I already said, that the we need to design a proper collection system where the gases that are generated in the landfill and the leachate that comes out of the landfill, those leachate are carried. Okay, these are carried using certain drainage systems such as drainage or collection system, which are generally made up of geonets and geotextile. So through the use of geonets and geotextile, we design these collection systems where they carry the leachate and gas, and then it collects in a certain collection system made up of under drains, or certain gases are collected in tanks or whatever way. Okay. Okay. So now let us see what is a liner. A liner is a thick or thin layer having extremely low hydraulic conductivity. As I said, what is a liner? A liner is something which prevents the leachate to pass through it. Okay, that is a liner. Okay, something. So what is the most easiest example of a liner is nothing but a what? Nothing but a sheet of this tarpaulin sheet, whatever you see in the daily market. Okay, or a polythene sheet, whatever you see. Okay, that is nothing but a simple example of a liner. Okay, And then we have compacted clay liner. So clays, as you know, has very less permeability, right? Clays generally have very less permeability. So what we can do, we can use highly compacted clay layers, So if we compact clay layers, highly compact the clay layers, what will happen? They will have very less permeability, right? So we can use those compacted clay layers also as liners. Then, as I said, the most common HDP, high density polyethylene or polyvinyl chloride PVC geomembrane layers. They are nothing but sheets of geomembrane. They are generally black in color. Okay, black sheets of PVC or HDP. And at the last we have a geosynthetic clay liner. So what is a geosynthetic clay liner? Geosynthetic clay liner is same. In between you have clay sandwiched between two layers of geotextile. Okay, this is nothing but a geosynthetic clay liner. So these are already discussed in the main class, right? So we are just going having a recap of whatever is discussed very fast. Okay, then we will see next. So here you can see an example of single layer system. So what are single layer system? Single layer system, then what are double layer system? All these things are shown here. Okay, all these things are shown here. And single layer, double layer, for what purpose also? So it, the design also changes with the type of layer, number of layers, and also for what purpose you are using. Okay, for what purpose. So generally for municipal solid waste, it's fine to use a single layer system. But if you're dumping some hazardous material, okay, some toxic material, some industrial waste, say, okay, so that should be contained minimum using a double layer system, double liner system. Okay, two layers of thick layers of liner should be there. Okay. So here see, this single layer and double layer systems are given. Okay, in single layer you can see this hazardous waste is at the top, it's been collected, then you have leachate collection system, then you have compacted clay, and then finally you have the subsoil. And then in double liner system you have the hazardous waste you are dumping at the top, then you have the primary leachate collection system, generally it is made up of geonets or geotextile, then you have primary composite liner, generally GCLs, geosynthetic clay liner you have, and again you have one more collection system. Okay, if some leachate is gets escapes through that, still we are able to collect it. That's what means double safety is there. So then we can have a secondary leachate collection system, and after that we have a secondary composite liner. So like this, it's a double collection system. Okay, like that. Now, what are the basic properties that we should have for a geomembrane? So, physical properties: thickness, density. Thickness you should know. You have to determine density, metal flow index, weight, water vapor transmission, solvent vapor transmission. So, these basically are various physical properties. So, some of these properties we will see in detail, not all. Then mechanical properties, same as whatever we studied in case of geotextiles and geogrids, tensile strengths, here seam weaver, tear resistance, impact resistance, puncture resistance, friction, stress cracking, all these things. Then if endurance means what? Long term, what will be the how the performance of your liner is going to, or the geomembrane is going to change. Okay. So resistance against ultraviolet, radioactive, biological, chemical, thermal degradation, all those stuff. Now, what are the tests required for geomembrane? One is the strength test, right? Tensile strength test. Then you have to determine the thickness, then stability, mass per unit. All most of these are similar to the whatever we studied for your geotextiles and thing, right? Okay, then how to get this thickness? Okay, how to determine the thickness of the geomembrane that you have to use? That is actually determined from here. Okay, using this expression. So how we get this expression? We are going to see. Okay, so here you can see T is nothing but the thickness of the geomembrane uh, that you have to choose. Okay, and how do you have to find that out? We will see that later. Okay, we will see the complete how it is derived, and we will try to solve one problem also. Okay, just a few slides later we will see that. Now let us come to this water vapor transmission test. So this water vapor transmission test actually determines as how much water vapor, okay, how much water vapor is actually able to leak through the geomembrane. Okay, through the geomembrane, how much water vapor is actually lost. Okay, that is actually determined by the water vapor transmission test. So this apparatus you can see here in the image, in the figure. So you have a small container over which, inside which you have water. Okay, and then you cover the container with your specimen. Okay, your specimen, with your specimen geomembrane you cover them. Then as the time passes, you measure the weight of the container, the reduction of weight in that. So some of the water will be lost, right, due to evaporation. Some of the water vapor will pass through the geomembrane, it will be lost. So you need to determine the weight, the reduction in weight. So obviously if the water evaporates and comes out as water vapor, obviously the weight of that container is going to reduce, right? That is going to reduce. So that weight you have to measure with time. Okay, weight you have to measure with time. So I will just write the expression for you. So water vapor transmission is given by G into 24 by T into A. G is what? G is the weight change. Okay, you can see a graph that is given here. So from this time to this time, say how much weight change is there. Okay, is the weight change in gram. Okay, then T, you have time interval in hours. Okay, and A is the area of the specimen. This in meter square. So the unit is what? Gram per meter square day. Okay, this unit here, whatever expression I have written here, this the unit of that is this. Water vapor transmission, this is the gram per meter square day. Okay. Now from the water vapor transmission we can determine some other allied properties. Okay, just by using the WVT value we can determine some allied. So one is the permeance. So permeance is vapor transmission by delta P. Water vapor transmission by S into R1 minus R2. Now what is delta P? It is vapor pressure difference across the membrane. Okay, this is in mmHg, mm of mercury. Okay, mmHg means mm of mercury. S is also mmHg, and R1 is the relative humidity within cup, and R2 is the relative humidity outside cup. Okay, the unit is metric parms, PRMS, parms. Unit is metric parms. Okay, there one more thing we can get from here, that is your diffusion. Okay, this diffusion is also known as permeability. This is not the same as the other permeability that we study in soil mechanics. Okay, this is different. This is nothing but permeance into thickness of the geomembrane. Okay, the unit is metric parm mm. Okay, this is the unit. I will just yeah. So see, calculate water vapor transmission, permeance, diffusion. Okay, for this thickness is 0.05 mm PVC geomembrane. So we have 0.75 mm PVC geomembrane. The area is 0.0030 meter square. The relative humidity difference is 80% at 30 degrees Celsius. The test data is given in the previous slides. Okay, so test data is this one. So this is the test data you have for a specimen. Okay, so weight you have and the time lost in days you have. Okay, the time you have, and in other axis weight you have. Weight lost versus the time. Okay, weight versus the time. So how to find out the water vapor transmission? What's happening? Okay. Area 0.003 meter square. RH difference is 80% at 30 degree. 0.75 mm thick PVC tube. Okay, data given previously. So water vapor transmission is what? 0.216, that you got from the graph, divided by 40 times 24 times the area, 0.0030. So it will come as 1.80 gram per meter square D. Now how to find out the permeance? 1 WVT divided by 32, what the saturation vapor pressure. Okay, saturation vapor pressure times 0.80. This will come out as 0.0703 metric pounds. Okay, then we have the diffusion, 0.0703 times the thickness, metric pound mm. Okay, so this is also known as permeability, but this is the Fickian diffusion. Okay, not the permeability that we study in this, not equal to this Darcian permeability. Okay, this permeability is different, not the Darcian permeability that we discussed when we discussed the flow of liquid through soil. Okay. Okay, now see, now if you want to convert this permeability to Darcian permeability, that also we can do. Okay, that also we can do. So WBT is 1.80 into 1 by 20. So we have to just convert the units. Okay, one by one we have to convert the units. So this one comes as gram cm squared second. Okay, so one by one you have to convert the units, and the next for permeance also you need to convert the unit again. So this will come out as gram per centimeter square second mmHg. Okay, then next we have what? Permeability. It is 0.075 in centimeters. So 0.609 into 10 to the power minus 11 gram by per centimeter of the liner. Okay, just converting the units. Okay, just you do it yourself slowly one by one. You will see it's nothing. Just all the units we are converting one by one. Right. At 1609. So this you can write per cm. Okay, therefore hydraulic conductivity so mmHg we have to convert to mm of water. Okay, how to do that? 13.6 times water by mercury. Okay. So finally we have this is Darcian permeability. Okay, so this is Darcian permeability. So we convert all the units, and from this the same thing we can get the Darcian permeability as well the your Fickian diffusion. Okay, the this permeability what we are speaking about before. Okay. So now let us see this question. Consider a 7-meter geomembrane lined pond that is leaking liquid and or has rising gases from the subgrade soil. So both these things we have. So we have a geomembrane lined pond is there, and some amount of that pond is leaking some liquid below, and also some gases are also coming up. Okay, some gases are also coming released. Okay. The width is 200 meter with the grade downward from left to right as shown. Okay, so this is the grade. So this is this grade, this direction 0.5% whatever it's given here, that that is told in the question, this grade. And grade is there from left to right, so that the water or whatever this liquid is leaked liquid flows at a grade and then finally comes out from that under drain. Okay, this under drain. Okay, this under drain. And how will it flow? It will flow through this geonet. Okay, geonet or this geocomposite, it's one layer of geonet or geocomposite given, which will carry this leaking liquid, and it will drain it to the under drain. Okay, a high estimate of geomembrane leakage is 5000 liters per hectare day. Okay, this is the amount of leakage that is happening per hectare per day. The proposed under drain to be used is 6.3 mm thick biplanar geonet with geotextiles bonded to each surface. So that we already do. You can now at this point you are, I am sure that you are able to imagine how it looks like, right? So you have a geonet. Okay, you have a 6.3 mm geonet, and at the top and the bottom you have layers of your geotextile that is bonded to each other. Okay, so it is sandwiched like that. So what purpose does this geotextile, this and this geotextile serve here? What is the purpose of using this geotextiles here? What is the purpose of using this geotextile? So the geotextile here acts as a what? Filter, right? Filter. It acts as a filter. It allows the water to pass through. Okay. And so we need to find out the factor of safety of this geocomposite for the liquid transmission. So whether it is able to properly pass the liquid or not. And what about the gas? What will happen to the gas? The gases will also come out like this and then vent out. Okay, vent out. So you are our the main point of concern here is that we have to find out the factor of safety for this geocomposite liquid transmissibility. Okay, whether is it able to transmit, whether it will be able to transmit the liquid easily or not. Okay, that is the main point of concern. Okay, so first what we know the flow rate that is given. Okay, the flow rate we know. What's happening? Why? Yeah. The flow rate we know. So this is given, right? So equal this is how much? 5 into 10 to the power minus 4 square. So just convert the units. Okay. 0.5 times 200 times 1. So 200 is what? 200 is the width and times per meter length, but out of plane direction. Okay, out of plane direction, out of the plane of the screen. Okay, this out of the plane of the screen 1 meter we are taking, so we'll get in meter cube per day. Okay, 200 is the width, that is also given in the question. Then we convert the units again to minute, so we'll get 6.9. Okay, now what is the slope that is given? This slope of flow, gradient of flow, this given is 0.5%. Okay, nothing but 0.05. Okay, then we write the flow equation. Q is K I A. K I A. What is the area? How can we write the area? Where you can thickness times the width. Okay, thickness times the width. Thickness, this thickness and width are the for the this whatever geocomposite we are using, that is that. So KT is the theta required, right? CT required is Q by Q per. Okay, so this is the required theta. Okay, required theta. Now we need to get what? We need to get the what is the theta of the geocomposite or geonet that you are using. Okay, so for that you know, if you recall from the previous class, you might remember that we had this theta value here, and we had vertical pressure here, and we had some graphs like this, right, for various I values. It is the gradient values. We had some graphs. So these are what? These graphs are obtained from what? These are obtained from the test data. They are obtained from the test data. So for the geonet what you are planning to use, for that you will be having this test data, and from that for a particular vertical pressure you will be able to determine this theta value, allowable theta value. right? So what is the vertical pressure? Vertical pressure is what? The height, this height 7 meters, 7 meters times water is there, so gamma w is what? 9.81. 7 times 9.81, so approximately 70 kPa you can take. So from test data we'll get theta. So this I have not drawing, so you can use the data that is given in the previous class, that only you can use in this case. Theta reliable is for this much is, and I as 0.005. For these two values you have theta reliable as 12 cube per. Okay, therefore factor of safety what is the theta required? So how much is it? 43. Okay, so we can safely use. Okay, so we can safely use this particular geonet for this purpose. Okay, we can safely use this. Okay, so now let us see next thing. Plans and delete. Next, let us see this geometric considerations. So what is this say? You have to construct aligned system like this. Okay, line system like this or whatever. Okay, say you need to construct this for holding water or whatever it may be. Okay, like this. Okay, so you have some slight slopes here, horizontal is to vertical like this you have. So what is the volume of this structure? How do you determine that? The volume is nothing but so HLW minus SH square L minus SH square W plus twice S square HQ. Now what are these? V is what? The volume of the reservoir. H is average height. This depth. Okay, so I will erase this from here, else you will get confused. This H. W is width at ground surface. L is length at ground surface. S is slope ratio, means this ratio, the ratio of this here. Okay, horizontal to vertical, horizontal to vertical, this ratio, horizontal to vertical. Okay, this is the S is the slope ratio. Okay, so this is how we'll get the total volume of a reservoir looking something like this. Okay, now let's see this. A square area 125 by 125 meter is available. Good. Construct a reservoir to store okay, see how many liters, okay, this much liters, this many liters of industrial process water. So you need to construct a reservoir like this to store this much liter of industrial process water. Okay, so you have to obviously you need to construct a lined system so that the industrial process water does not leach into the ground. Okay. Estimated slide slope is 3 horizontal is to 1 vertical. What is the required average depth? So how much depth should have if you have this criteria? Okay, so what is the v is this much liter means such how many meter cubes, this is how much meter cube, how much in meter cube, tell me, this is how much in meter cubes, this much liter, this much meter cube. Now what you do, now you just put it in your equation, that is what 60,000 60,000 is equal to h times this 9 is what, s square. Okay, find it out, solve this and find out h. Okay, so you will get the average depth as 4.83. Just do these problems by yourself, try to solve this again by yourself. Okay, check that whether you are able to get the answer or not. Just a second now. Yeah, so I was telling you right that about the thickness of geomembrane, right, in the first second initial slide. So I said that we will see that how we get the thickness of this geomembrane. So say mm, how to say you have, as we discussed before, say you have made a lined reservoir like that. Okay, so you have constructed a lined reservoir, you need to construct a lined reservoir using your geomembrane like this. Okay, now due to the load that is coming, here on the geomembrane, so initially it is straight, right, it is straight, but due to the load that is coming, what can happen, you can have some bend like this here, like isn't it? So due to the load that is coming, it might not be straightened. It will be some, it might get distorted like this. When it gets distorted like this, the tension that develops in the geomembrane. So obviously see some a sheet, how wait, just a second. So you have a straight sheet like this, okay, you have a straight sheet like this. Now due to the load, what happens, it is getting distorted like this. Now when it gets distorted like this, the strains are generated, getting mobilized here. Okay, due to this strain, some tensile forces will be getting generated in the geomembrane. Now these tensile forces that are getting generated, these should be less than the strength, tensile strength of the geomembrane, right? It should be less than the tensile strength of the geomembrane. So that thing, that mechanics actually we are going to see here. Okay, that mechanics we are going to see here. Okay, so say you have, okay, so I am just drawing this portion, okay, this portion, okay. Say due to some it gets distorted, so that half I am drawing. So it is something like this. So say this height is delta H. So here also you are having some pressure, right? Obviously vertical pressure is there here, downwards everywhere. So that vertical pressure is there, the normal stress. Now, now it now it bends at some angle beta, say. Okay, it gets distorted at some angle beta. Now due to this, what happens, some tensile forces are going to get generated here, some tensile forces are going to get generated, isn't it? Some tensile forces are going to get generated. Now these tensile forces, it is said that it will get mobilized across this distance x. Okay, this distance x, these tensile forces are going to get mobilized across this distance x. Now how do you find that out? Now say we have like this, so this is the tension. Okay, so here you are having this normal stress that is acting, right? Now also along the normal stress, you will be having some frictional resistance that develops here, fu delta. Now at the lower phase also, you will be having some frictional resistance that is developing. Okay, now frictional resistance that is developing, all right. And this, so this is this delta, whatever I am writing, this frictional resistance is developed from the normal stress, and one more frictional resistance develops. This frictional resistance is nothing from this tensile stress mobilization, and this tensile stress actually gets mobilized over a distance x. It does not get uniformly mobilized, it gets mobilized in a triangular fashion, okay, like this. So this value is what, this value is twice t sine beta by x. Now how, from where is this t sine beta coming? So this t has two components, right? This and this. So this is t cos beta and this is t sine beta. So now this normal stress, whatever it's getting mobilized in this part, this is also going to create one more this frictional component, flt. Okay, so all this, if we equate together, if we will get the expression of this thickness, okay, thickness of the geomembrane. Now if we equate, now if we do summation fx equal to 0, so what you will get, t cos beta is equal to f u delta, u sigma, f l sigma plus f lower due to tensile strength, tensile mobilization. These things you will get. So you have delta n. So what is this? Delta n tan delta u into x, right? Plus delta n into tan delta lower delta into x, plus the area of the triangle, half into twice t sine beta by x into x delta l. Now what are these deltas, you will see. Okay, this is the total shear resistance that This is the what total that balance the horizontal component of the tension. Okay, now what is T? But what is T? T is nothing but allowable stress in the geomembrane times the thickness, so we can, therefore we can get T is tan delta U allowable cos beta sin beta. So delta U is what? Delta U is the frictional resistance between the geomembrane and whatever material is above that. If it's waste, then the delta between the waste and the geomembrane. If it's water, it will be zero. Okay. If there is soil, then it will be something else. The frictional resistance between the soil and the geomembrane, whatever. Same goes for the delta L. Same goes for the delta L also. Okay. So I will just write this for you so that it's easier for you to look later. So beta is the settlement angle. Settlement angle mobilizing the geomembrane tension. Then you have Fu delta is the shear force above the geomembrane due to this doesn't occur for liquid on thin soil covers or thin soil covers. Okay, if you have liquid, obviously this delta is going to be zero, so it becomes zero. Due to what? Due to vertical component of tension, just T. Deltas are what? Angle of shear resistance between geomembrane and adjacent material, and X is the distance of mobilized geomembrane deformation. Okay, so these are all the terms. Now what are the general ranges of all these values? That also I will give you. 2200 kp, that is approximately 2 to what, 2 to 10 meter of liquid. What is water approximately? Beta is what, 0 to 60 degree. X is generally 15 to 100 mm. The allow is approximately 6000 to 30,000 kPa. Depends on what quality of geomembrane, what quality of geomembrane you are using. Okay, it depends on that. Not soiled. So these are all determined from lab tests. Okay. Okay, so these are the general ranges of all the values that we use. Okay. Now I will give you a problem. Please try to solve this. Please try to solve this problem. All the things are given to you. Okay, just directly you have to use, put the values and find out. Determine the thickness of a geomembrane to be used in a containment of a 7-meter deep water reservoir where the settlement over a backfilled collector pipe could result in a 45-degree settlement angle. Beta is given, depth of water is given, that means you know the pressure. The geomembrane is textured LLDP of 8000 kPa allowable stress. So allowable stress is given. There is only a thin cover of soil over the geomembrane and a non-woven needle-punch geotextile is placed beneath it. Estimate the mobilized distance for linear deformation. Estimated mobilized distance for linear deformation x is 50 mm. So you need to determine the thickness. So directly just put the values and you will get it, right. So delta n is what? 7 meter times 9.81, so approximately 68 point times. So delta U will be 0. Okay, alright. I hope you are able to understand. Directly just put the values when you get f3 meter. Okay, so this is the required thickness of the geomembrane that we have to have. Alright. Now you have, next is the factor of safety. The factor of safety of the slope. So you have placed the geomembrane like this. Okay, say you are making a reservoir, so it is like this, right? As we solved the found out the volume, so it's like this container, this like this, then this goes up. So these slight slopes that you have, that's the slopes that we have, that slopes are what? That slopes are finite slopes, because they are small slopes, those are finite slopes. Now say you lay the geomembrane like this over a large huge area, like in a hill slope, say you lay geomembrane, so that is what? Infinite slopes. In both these cases the factor of safety is different, so this already you know from your basic soil mechanics how to get the factor of safety of finite slopes and infinite slopes. The same thing is actually given here. So given it. So this first thing is a infinite slope. So infinite slope is there. So we have a finite slope here. So the infinite slope here. So you have a large slope and you have a geomembrane placed. In that case, what will be the factor of safety? Now, so you have a finite slope. So you have a finite small slope where you have placed the geomembrane, and over the geomembrane you have a soil cover. So you have placed the geomembrane. Over the geomembrane you have a soil cover of a certain thickness. You have a soil covered of a certain thickness, uniform thickness soil covered you have over the geomembrane. In that case, what will be the factor of safety? And again, if the soil cover is tapered, in that case, what will be the factor of safety? So in the first case is normal, it's same as the infinite slope. How to find out the factor of safety? Same as that. Okay, you have the geomembrane, you have the covered soil above it, it's infinite slope, so no issues, directly we'll get that. Now if it is a finite slope, then what happens? In case of finite slopes, you can see one here, there are this wedge is different and this wedge is different. So this wedge is known as the active wedge. Why it is the active wedge? Because it is moving, right, like this, it is moving away downward towards, this is the active wedge. And this triangular wedge that you see here, this triangular wedge that is in the bottom, the triangular wedge is the passive wedge. Okay, this triangular wedge is the passive wedge. Here, what? The passive resistance develops, right? So passive resistance develops. So these two wedges, the mechanics is solved, and we finally find out the factor of safety. So let us see. So directly I will give you how we can actually do that. So for infinite slope, what is very easy, right? For infinite slope, you already know factor of safety is what? Resisting force disturbing force. Right? So this is the what? Friction angle between the soil and geomembrane. Okay, and this beta is nothing but the slope angle. All right. So what is the resistance? So resistance force is the frictional resistance that develop. A disturbing force is what? The sine downward component, this component of the weight, right? So n is the normal force, is W cos beta. Therefore factor of safety is what? Tan delta by tan beta. Okay, this is the factor of safety in case of an infinite slope. Okay, now what is the case of finite slope? So in finite slope we have two cases. One is uniform soil cover, another is a tapered soil cover. Okay. So we have the weight of the active wedge. So I am not going to detailed derivation. I will just give you everything. Give the expressions. Okay, this is the factor of safety, and how to get the all the quantities. So A is okay. A is so match all these things with the book. Okay, in book everything it's given. So there might be some mistakes while I write it here. So please verify all the expressions and everything from the book. Okay. It is WA. Active wedge. WP is total weight of passive wedge. Na is effective normal force to the failure plane of active wedge, and NP is similar normal force to the failure plane of passive wedge. Okay. Gamma is unit weight of soil covered. H is thickness of the covered soil. L is length of slope. Beta is slope angle. Delta is in friction angle. So many things, right? Ca is adhesive force between covered soil of the active wedge and geomembrane, and Ca small ca is same adhesion between same okay, adhesion. Ca is the adhesion, and so other is the cohesion. Okay. Did I miss anything? Nah. Okay, so match all these expressions in the book. Okay, see in the corners book, everything is given very nicely and properly. Okay, if you see, I don't. You should see, you should see the book and study from the book all these things. Okay, it's very difficult to write the all the expressions here, right? So I may make some mistakes. There is no guarantee. So that's why I'm saying that please see the book. Okay, we'll get everything properly. Then again we have what tapered covered. So if you have tapered covered soil, WA changes. So I guess beta by 2. Okay, check the expressions. Okay, check the expressions. Safety is minus. Similarly, similar to the previous one, here also we have ABC like that. What's the time? I hope we have. Yeah, we have. Okay, so check all these expressions in book, huh? Now let us see this problem. Given a 30-meter long slope with a uniformly thick covered soil of 300 mm at a unit weight of 18 kilonewton per meter cube. Okay, so we have a 30-meter long slope, uniform thick covered soil, 300 meter uniform cover, and unit weight is 18 kilonewton per meter cube. The soil has a friction angle of 30 degree and zero cohesion, that is sand. The covered soil is on a geomembrane. The direct shear testing has resulted in the interface friction angle between the covered soil and the geomembrane of 22 degrees and zero adhesion. What is the factor of safety value at a slope angle of 3 horizontal to 1 vertical, that is 18.4 degree. So you need to find out the factor of safety here. What is the case? This case is of a finite slope with uniform soil cover. Okay, so just try to use the these expressions and solve it. Okay, try to use whatever expressions I just wrote down here before. Just try to use this and solve. Okay, just write it down first at some place. Okay, so what we need to do, all the values are given, huh? Just we need to directly put the values and solve, find it out. Just give me 1 second now. Yeah. Yeah. So what I was saying, yeah, directly see all the values are given. Directly we'll just put the values and find out the thing. Okay. So what is WA? Okay, so this is 18. Yeah, this is what 18.4. Just put all the values. If you put here, you will get. Okay. Similarly, NA. I'm just solving it for you. Just you do it yourself, okay? If you do not do it yourself, you won't get the feel of these problems, okay? So I'm requesting you again and again that please solve these problems again by yourselves. Because the vector safety concept is 1.25. Now say the slope would have been infinite slope. Say just for example I am saying, say the slope would have been infinite. Then how would have would you solve the problem? Okay. Now one more problem, same problem, but now it is a tapered case. So I'm just not going to read the problem. Just try to solve it by yourself. I won't read the problem. Try to see if you understand or not. Try to see if you are able to understand the problem or not. Same problem, but now we have a tapered thickness, tapered covered soil. Instead of a uniform covered soil, now we have a tapered covered soil. Okay, see 30 meters long slope, tapered thickness covered we have. Okay, cover slope 150 mm at the crest, extending at an angle of 16 degrees down. Okay, soil thickness at the bottom is 300 mm. Unit weight of cover is same, 18 km per meter cube. Soil friction angle is given. All right, question is zero. Covered soil is on a geomembrane. Direction testing same, 22 degrees, zero addition. Other things are same, but now just we have this tapered cover instead of a uniform covered thickness covered soil. Now we have a tapered. So what the same the respective parameters you have to find out. See, I am not writing the expressions. You do that, huh? You write it and check. And A, B, C again. We have to find it out for this to come on test. Factor of safety. Okay. So So you're seeing that for a tapered cover, you are getting a higher higher factor of safety. All right. So this was all about this factor of safety in slopes thing, right? Now next we will see the case when we have this run out trench, run out and anchored trench case. Okay, this run out and anchored trench case. So let us see that now. Next. So what is the run out? So see, now the geomembrane you are placing like this, right, in the slope. So you are placing the yeah. So you are placing the geomembrane like this. So this geomembrane, it's generally placed like this. Okay. So this is the slope, and this geomembrane is placed, and so here we have the covered soil like that. Covered soil like that. So this distance, how much you have to put, is LR naught, that you need to find out. Now in some other cases, what you also can do is that you can anchor this geomembrane downwards into the soil in an anchor trench like this, like this. You can anchor it into the soil so that when it does not, you understand that why we are doing that. We have to find it is similar to the concept of the embedment length. Okay, embedment length beyond the active field, so that we solved in case of reinforced soil walls, right? If you remember embedment length, so similar, thus analogy is same. Why to provide the embedment length? So that the geomembrane does not get comes out with the load. Okay, you need to have optimum length, or what you can do, you can have optimum length, and then further if you want to make it more secure, you can have a tug, you can put the tug, you can tuck the this you can tuck the geomembrane into an anchored trench, or you can anchor the geomembrane in a trench. Okay, you can tuck the geomembrane into the trench. Okay, that will further secure it, right? It is going to secure it more, secure the geomembrane in position more. So that is, these are the two things. So how to determine this anchor trench and this run out length, that let us see. The first is the run out, just run, there is no anchor, there is no anchoring, just directly it is just placed like that, and above that your soil is there. So this optimum length, that length whatever you have to put, that you need to find out. In that case, what we have to do, similarly, for the run out section, okay, for run out, just say we run out, the run out section summation fx equal to 0, let us do. Then T allowable into cos beta is same fu delta plus fl delta plus flt. Fu delta is what? Sigma 10 u lr naught plus n 10 delta l lr naught plus 0.5 to T allow sin beta lr naught lr naught is equal to T allow cos beta minus. Okay, now what is this T allow? T allow is what? Sigma allow times T thickness. Alright, so this is the LR naught. This is the LR naught. Our next case is where we have the anchor also. For anchor trench at end of run out. Okay. Now for the anchor trench you are writing. So similarly, this you will have similar. Okay. Additionally, you will have this minus PA plus PP. So what happens? So here some this passive resistance has developed. So this way you have a passive resistance, and this side you have an active resistance. Okay, this actually developed. So obviously this passive is higher, so it actually helps us to hold the that geomembrane in position. Okay. Okay, and PP is, all these things are shown in the figure, huh? So there should not be any confusion about this. What is DAT and all, everything is shown. Okay, see, everything is shown in these figures. All right, so there should not be any issue. Okay, so this is all. This is how we get it. All right. This is when only we have the run out section, and this is when along with the run out we also have it anchor trend. Okay, this is when we have anchor trend. This is only for the run out section. Okay, so let us see a problem. Write down the question. Consider a 1 mm thick LLDPE geomembrane with a mobilized allowable stress of 5000 kPa, which is on a 3 horizontal to 1 vertical slope. Determine the run out length to resist this stress without use of a vertical anchor trench. Use 300 mm covered soil of 16 kilonewton per meter cube and 30-degree friction angle with the what? With the what? With the geomembrane, right? So this is the question. We need to find out the round out length without the use of vertical end. So without the use of an anchored trench, how much would be the run out length that you have to find out? So first we have a T allowable tensile strength in the geomembrane is nothing but sigma allowable stress times the thickness, which is 5000 times 0.001. LR naught is what? T allow by cos beta minus sin beta L. Okay, so LR naught is 5 0 plus 1030. So if you put the value, you will get 3.83 divided by 2.6. So LR naught is 1.34 meters. So this is the runout length that is coming for this case. So now let us see one more example where we have this anchor trench. Just a second. So I will wait, just a wait. I will give the values. Yeah. Okay. Give the values. So T is 1 point thickness is 1.5 mm. Sigma LR is 16,000 kPa. LR naught is 1 meter. Then thickness of cover soil is 300 mm. Gamma is 16.5 kilonewton per meter cube. Delta L is 30 degrees, Y is 35 degrees. Okay, so these are the given values. Same T allowable is equal to sigma allowable times T. Fu delta is what? Sigma n 10 delta U. Not so delta U is 0, so this is 0. Now FL delta this is, I think this is 43. Check this value, how much is it coming? 43.7, I think. You check this, 43.7, or how much it should check this. Then what? So LT, then you have to find out PA. Squared. 40 square 80 plus 1.40. So you got seeing, you got getting in terms of the depth of the trench. Similarly, PP we will also get in terms of the depth of the trench. So 8.25. So these all these expressions you might be thinking that you have to remember all these things. This is not that, na. If you see if you see what if you understand whatever it's happening, you can derive the equations by yourselves in one line only. You don't need to remember all this what is the expression or what is PP. So all this you know already, right? Whatever it's happening, half into gamma 8 into dt plus sigma is the normal stress times the ka times the dat, right? So you don't need to remember all these expressions. These are obvious expressions, right? I hope you understand it. Okay, next we take summation fx equal to 0. So we put all the values. No, this is 4.37 only, I think. Now so you get this expression, right? Now for various values of lr naught you will get various value of dat, right? So you can adjust it, right? Now for lr naught equal to 1 meter, it's given, let's say it's given in the question, so we'll take lr naught equal to 1 meter. So if lr naught is 1 meter, you will get this expression. So from here dat will similarly 0.57 meters, so you can take as okay. So this much dat you are getting for lr naught. So what we can do is that we can finally prepare a chart. So say for dat equal to 0.5. Okay, so we will get lr naught, then here you will have t allow. So like this very s values we can get. Now similarly if we have, you can change either dat or you can change lr naught. Okay, we have this expression is both, right? Either you can put dat and find lr naught, or you can find lr, you can put lr naught and select a dat. So ultimately it's a design problem. It depends upon you how you find everything out. Okay, right? It is a design problem. So either you put you first you choose dat and then you find dlr naught, or first you decide one dlr naught and then you find a dat. That you get, that depends upon you. Then again for dat equal to 1, here you can have again various combinations of dlr naught and t allowable. So like this what you can do, you can get some graph like this, right? lr naught meter, and you can get t allowable here, newton per meter, and then some graph you will get like this. Okay, for various, say this is dat is equal to 0, this is dat is equal to 0.1 meter, this is dat is equal to 0.2 meter, like this various graphical. So for any value you can find it out directly. What should be the lr naught for that particular t allowable of the geomembrane for that particular dat, like that you can find it out from the graph. Okay. Now, so this was one thing, right? So now we discussed one thing where we found out the factor of safety of slopes, right? If we found out the factor of safety of slopes for infinite slopes or finite slopes, we found, just saw some slides back how to calculate the factor of safety. All these things we saw. Now if geogrid is also used, if geogrid reinforcement is used in slope with geomembrane, okay, then what will happen? If geogrid reinforcement is also used with the geomembrane, okay, to reinforce, to reinforce the slope we are using a geogrid reinforcement also. Then what will be the, so these terms WA, NA, WB, this will be same. Okay, so just in the slope what we are doing, you are placing a geogrid reinforcement. Okay, you are placing a geogrid reinforcement. In that case your A will change like this. T sine beta cos beta. This T will come, and what is that T is, you will see. C is, again I am saying, please verify the expressions from the book. Okay, don't trust these expressions blindly, whatever I am writing. Verify all the expressions from the textbook. So, and what is T? As I said, this T, what are this T? T is T ultimate by the cumulative reduction factor for the geogrid. For the geogrid. So this you already know what is cumulative, what is the cumulative reduction factor, and all those things you already know, right? Right, so that was also with this what we will do, we'll end today's session. So just basically we ended our course with this last discussion about the geomembranes, and then basically the next session, that is on the Sunday, on the 20th of October, we are going to have a last revision session where we will just skim through all the topics from the first session to the last till today's session, whatever we have studied. Okay, we will just go briefly in 1 hour duration. We will just skim through all the topics. So link will be same, not tomorrow, sorry, summary session is Sunday. Okay, Sunday 20th October 2023. Time I think it was 3 to 4 p.m. Uh, please pay attention to the pay attention to whatever this your announcements that are posted in the portal or in the discussion forum of the NPTEL by the NPTEL team. Just pay attention to that. As far as I remember, it was 3 to 4 p.m. but I am not quite sure because I don't remember what time I had chosen. So okay, so see the NPTEL announcement later this week to confirm the timing. Okay, but date is confirmed. 20th, that is next Sunday, the coming Sunday on the 20th of October. We will having a 1 hour discussion session. The time, as far as I remember, it was 3 to 4, but I'm not that sure. So just please pay attention to the your please have a look at the announcements that will be that will be put by the NPTEL team a day prior. I think a day prior to the class they put, maybe in Saturday, on the next coming Saturday they're going to put. So just pay attention to that, what time is mentioned. And as far as I remember, to 3 to 4 only. Okay, so we'll meet on Sunday just for 1 hour. We will revise everything and then we will just close this course for this semester, and I hope that you have prepared well for the exam. You are preparing well, and please just go through whatever questions, whatever things were discussed by Professor Rajagopal in the main the classes. Please solve all those problems, and pay attention to all the concepts that were discussed by Professor, so that you can perform well in the exam. Okay, and solve all the assignment questions properly and nicely. And I am hopeful that I am sure that you are getting good points in the assignments also, and I am sure that you will perform well in the exam also. Okay, so with this we will wrap up today's session, and we have 4 minutes remaining, so I will be here for the next 4 minutes. If you have any doubts, you can ask me, or if you don't have, you can leave the session. All right, so thank you so much for attending, and we will obviously meet on the coming Sunday. We will have a 1 hour discussion, 1 hour wrap up session. We will summarize everything in 1 hour, and then we will close this for this semester. Okay, so thank you so much for attending, and have a very good evening. I'm here for next 4 minutes. If you have any doubt, you can ask me. If not, you can leave. All right, I will just turn off my camera, but I'm here. Okay, if you have any doubt, you can write in the chat box, or you can just turn on your mic and ask any question if you want. So I think I can end the session now. Okay, ending session in 5, 4, 3.